Now that we're fairly comfortable with confidence intervals, we want to go back and take a look at what would happen if we wanted to test a claim instead of find an interval. So in this case, we're going to go back to one sample, and we're going to be dealing with means and proportions, and in this case, we're going to do some hypothesis testing. So I strongly encourage you, before you watch this video in its entirety, I encourage you to complete section 10.1 in your Hawks certifications, because that is going to give you the overall understanding of hypothesis testing. You should do that before you do this video, otherwise it's not going to make quite as much sense to you. I'm going to give you a little bit of an introduction before I take you into the different types of testing. So let's take a brief overview of hypothesis testing. Again, it would be beneficial for you to complete section 10.1 before you try any of the practice questions in this video, which are from sections 10.2 to 10.4. This first slide is basically a review of 10.1, so hopefully you understand all of these concepts already. The first thing that you need to do is read whatever question you're being asked. And I would argue that actually step 2 has to come before step 1. And step 2 is determine which distribution to use for the test statistic and state the level of significance. So really what you're going to do is read the question and determine, do you have a mean where sigma is known? If so, you're going to use a z-test or a z-score, and of course the normal model. Do you have a mean where sigma is unknown? Well, then you're going to find a t-score and use the t-model. If you have a proportion, you're also going to use a z-score. Then you're going to state the null and alternative hypothesis. So the null hypothesis is typically stated as h sub 0. And then the alternative hypothesis, which is also sometimes called the research hypothesis, is h sub a. And I always tell my students that the null hypothesis just assumes the status quo. It assumes that everything is the same as it always has been. If I always have about 85% of students pass my class, then that's going to be my null hypothesis, is that 0.85 or 85% of students are still going to pass my class no matter what. Now let's say I'm making changes to my class to hopefully make my class better so that more students will be successful. Well, then I might test a hypothesis that says that more than 85% of my students are going to pass. So that alternative or research hypothesis would be that proportion would be greater than 0.85. So I would be testing whether or not the improvements that I've made to the course have increased the percentage of students who are successful. So that's all in parts 1 and 2, which all kind of smush together really into one big step. Step 3 is to gather your data and calculate the necessary sample statistics. So again, the necessary statistics would be either a z-score or a t-score. And then we're going to draw a conclusion and interpret the decision. So there's 2 ways to draw a conclusion, and one of them is using a rejection region. And you'll find that I'm not going to take you through that value, even though it actually is an easier way to visualize what's happening. Typically, that's only used for research articles. So quite often you will see just the p-value, which is the value that we are going to focus on in this class. So we're going to draw a conclusion and then interpret the decision. So what we're going to do is we're going to find a p-value. And the p-value is just going to be the probability given our z-score or t-score and given our alternative hypothesis. So let's say I got a z-score of 1.37 and my alternative hypothesis was greater than, that's a right-tailed test because I'm finding the area to the right, well then I'm just going to use Excel to do the norm norm dist of 1.37, comma 0, comma 1, comma 1, which of course is going to, on my picture, take the area of 1.37, and this would find it to the left. I want the area to the right. I want all of this. I want that probability. That's going to give me my p-value. And what I'm going to do then is draw a conclusion based on the p-value. So if my p-value is less than alpha, alpha being my significance level that we're very familiar with now, if p is less than alpha, I am going to reject the null hypothesis. So essentially what I'm saying is if I get a very small p-value, then I'm going to say, well, it can't be true that 85% of students pass. It must be true that greater than 85% of students have passed. Now, if p is instead greater than alpha, then I fail to reject. So notice I didn't say I'm accepting the null. I'm just failing to reject it. I'm saying, hey, you know what? It could be true, but based on the data that I've collected, I don't have enough evidence to say that. So it might be that you're still a little bit confused, and that's okay, because we're going to go through some examples together which will help it to make sense to you. But again, keep in mind, always equal, most often equal, I guess. I would say 98% of the time equal, and then this is going to be based on the context of the question. So let's take a look at our first example. Let's take a look at our first example. And as you can see, I already have some values in over here, and that's okay. Let's just focus on how we would work through this ourselves before we talk about how you can hack Excel like I did. So there's a lot going on with hypothesis testing. So if you look at this and you kind of want to cry a little bit, it's okay, because it is kind of difficult to get your brain around. But the good news is once you get used to it, you will, it will just become easier and easier for you. So again, what I'm looking at here is a question that says the mean age of women in California is higher than 26.5 years at the time of their first marriage. Surveying a simple random sample of 213 newlywed women in California, the researcher found the mean age of 27 years. So as you're reading through this, you should be thinking about, what's the mean age that I'm expecting to happen? What's the sample mean that I have found? What is the standard deviation of the population? What is the sample size? And then of course we're going to be writing our hypotheses. And our null hypothesis is always going to be the same as the population mean, or what we expect the mean to be. So it says the researcher claims the mean age of women at the time of first marriage is greater than 26.5 years. That, to me, anytime you're given that direction inside of your question, that's your alternative hypothesis. The mean is greater than 26.5 years, which means I'm expecting 26.5 years. Now, some textbooks will show this one as less than or equal to 26.5. There's a lot of debate as to which is the more correct way to write it. I have always written it with the equal sign, and that is what your textbook will do as well. Now, we have a simple random sample of 213 newlywed women. The researcher found a mean age of 27. So that is the sample. That's X bar. How do I know the difference? Because that is what the observer or the researcher observed. It is a sample. It is sample data, 27 years. The population standard deviation is 2.3 years. So we have all of the information that we need. What we need to do now is make some sense of it. So there are two ways to determine a conclusion to a hypothesis test. There is using the rejection region, which is a critical value, and then using the p-value. Now we're going to focus on the p-value in this course because that is the more common of the two that you will see most often. But I am going to show you one with the rejection region. I'm going to show you this example in both ways. And then for the rest of the examples, we're just going to look at a p-value. So the z-score is required either way. And so as you'll notice, I've got all of this going on over here, which is great, but you need to know how to do this yourself too. So I'm going to just work through this from the start. How do I find a z-score? I take the observed, which is the sample x bar 27, minus my hypothesized value 26.5. So that's my expected value. This value in your hypothesis should always be that second value in the numerator. Then I'm going to divide it by the population standard deviation. Notice I'm putting that in parentheses, 2.3 divided by the square root of the sample size, which is 213. My z-score is 3.17272, etc. Now, that's a very high z-score. Now I'm going to look at this two different ways. I'm going to look at the critical value and I'm going to look at the p-value. So let's look at the critical value first. And again, this is not the way that we'll typically do it. If I looked at the critical value, I'm going to find some number. So 3.17 is like all the way over here, right? 3.17 is my z-score. I'm going to find what is called the critical value for the rejection region. And the critical value for the rejection region is, because this is a right-tailed test. And how do I know it's right-tailed? Because if you'll notice, my alternative is pointing to the right. And so for a right-tailed test, I want to just take 1 minus alpha. So I'm going to here take norm.s.inverse of 1 minus alpha. Oops, 1 minus 0.05. So that's 1.648. That number is somewhere over here. So 1.6458. That number tells me that because it's a right-tailed test, anything to the right of that number is in the rejection region. And the rejection region says that if your z-score is in that region, then you should reject the null hypothesis. So if I didn't need to use a p-value, I would be done with this question. I would say, based on this data, I can say with 95% confidence that there is sufficient evidence to support that the researchers claim that the mean age at first marriage for women in California is higher than 26.5 years. Again, if I reject the null, which is what I did, I'm supporting the alternative. So notice when I said my conclusion, there's evidence to suggest that the mean age of first marriage for women in California is higher than 26.5 years, is just this alternative hypothesis in words. So now let's take a look at the p-value, because typically we don't use the rejection region. So I would go straight to the p-value. Now the p-value is pretty straightforward. If we find our p is less than our alpha level, then we're going to reject the null. And that, of course, means in favor of the alternative hypothesis. If we find that p is greater than alpha, we're going to fail to reject. So let's see what we come up with. What is our p-value? Our p-value is the probability that our z-score is, in this case, greater than or equal to what we have found. So we want to find that probability. So that means I'm going to take, because it's right-tailed, I'm going to take 1 minus. That's what we've already learned how to do. To the right is 1 minus. And this is norm S dist of my z-score. And then cumulative, you betcha. So that z-score, or that p-value, is very, very small, 0.000755. Is that less than alpha? Well, we already said alpha. Oh, I didn't write it down over here. 95% is my confidence level. Alpha is 1 minus my confidence level. So 1 minus 0.95, that's where I got 0.05. I apologize for not talking about that before now. So alpha is 0.05. Obviously, this number is less than 0.05, and so again, that tells me to reject the null. Now, let's talk about how I hacked Excel over here. Obviously, I've created a space for mean, a sample mean, population standard deviation, sample size, and alpha. And then, of course, we have our z-score, which is the exact same thing that I did here. I just pointed it to the correct cells instead. The left-hand critical value would be the exact same guy as this one, except over here, which would be negative 1.645. And as you can see, I just took norm S inverse of my alpha level, but the right critical value would be 1 minus the alpha level. And then for a two-tailed critical value, this one gets a little bit tricky, so we will do a two-tailed test together. Instead of putting all of alpha into one side, a two-tailed test would put half of alpha in each tail. So we'll take a look at that one when we get to the end. But that's how I did that for the critical value. So you're welcome to use the critical value, of course. Typically, though, I'm going to be looking at the p-value, as I said. And so for the p-value, it's norm dist, and then our z-score into the left. So norm S dist is what I used, either one. Right-tailed would be 1 minus, and then two-tailed, I got a little bit tricky, and so again, I'll take you through that one when we do a two-tailed test. Let's take a look now at a different test. So this is still a hypothesis test, but this is for means with sigma unknown. And in the last test, we had a right-tailed test, and in this test, we're actually going to look at a left-tailed test. So let's take a look at the question. It says, nurses in a large teaching hospital have complained for many years that they are overworked and understaffed. The consensus among the nursing staff is that the mean number of patients per nurse each shift is 8. So that is what we're assuming to be true. That is our null hypothesis. Whoops. That the mean is 8. So again, the null is h sub 0, and then the alternative is what we're going to test. The hospital administrators claim the mean is lower than 8, so that tells us the alternative hypothesis. That's what we're testing, lower than 8. Keep in mind again that these two values are always the same. To prove their point, the administrators gather information from a simple random sample of 19 nurse shifts, so that's n equals 19. That's the number of samples. The sample mean, x bar, is 7.5 patients per nurse with a standard deviation of 1.1, and the administrator's claim uses an alpha of 0.025. So again, because we are dealing with S and not sigma, that tells us that this is a t distribution, not a normal distribution, which means when we're working through this, we should be using the t distribution and t inverse for any of the functions that we're going to use. So again, if we're doing this with a z-score, the z-score is observed, so our observed value is 7.5, so x bar minus mu divided by the standard deviation, 1.1, divided by the square root of the sample size, which is 19. So that's my z-score. So that's a very low z-score. So again, even if you're not using a rejection region, you can still think about what you've just found. Negative 1.98 is over here. That's very small. Now what I want to do is I want to compare the probability that I get that score or lower. So I want to find this area. And if that area is less than alpha, less than 0.025, then I will reject, otherwise I will fail to reject. So let's find the p-value. So again, the p-value would be finding that p, the probability that z is less than negative 1.98. And so I'm going to let, of course, Excel do that for me. So again, this is a left-tailed test because my arrow is pointing to the left. So I don't need any 1 minus here. I'm just going to find t-dist. And the t-dist is the z-score, the degrees of freedom, which is n minus 1, so 19 minus 1, and cumulative, which is true. So what I have found is a p-value of 0.0315. Now, what does that mean? Well, it all is based on alpha. So because we have an alpha of 0.025, remember that I said if p is less than alpha, we reject. Well, in this case, p, 0.0315, is greater than 0.025. P is greater than alpha. So that means I have to fail to reject. So what does that tell me to do? So this is the conclusion, is to fail to reject. But remember, what does that mean in context? I can't think and write at the same time. Sorry about that. Fail to reject. What does it mean in context? We can interpret the conclusion of failing to reject to mean that the evidence collected is not strong enough at the 0.025 level of significance to reject the null hypothesis in favor of the administrator's claim. So essentially we're saying we don't have enough evidence to say that the mean number of patients is less than 8. So for now, we're just assuming it is 8. So yay nurses, you were right. Now, again, it's okay to set up, as you're working through the certifications, it's okay to set up your Excel spreadsheet so that you can find your values quickly. But again, I'm just going to keep stressing to you that you need to also just understand what it is that you're doing so that when you do something like this on your project or on your forums, that you're not showing me my spreadsheet with a bunch of answers and then not even telling me which one the answer is. So make sure that you're able to just find the correct answer as we did here. Now, of course, I'm going to go through this on how I set up my spreadsheet. So my hypothesized mean is 8. My sample mean was 7.5. My sample standard deviation was 1.1. My sample size was 19. And then alpha was 0.025. Now, on this one, as you can see, I've given you a little bit of extra fun. That's just me being a math dork. But let's take a look at the functions that I've used in yellow. So in yellow, I've set up the z-score, which is the exact same z-score I found here. I just pointed it to the observed or sample mean minus hypothesized mean divided by the sample standard deviation divided by the square root of the sample size. The left-hand p-value is, again, we're using the t-distribution because sigma is unknown. This one is of J7 going to the left. To the right is 1 minus that. And then, of course, the two-tailed value, again, I'm going to wait and go through that with you on our next question when we look at a two-tailed test. Now, in terms of reject or fail to reject, again, this is just me being a math dork, but if you're a math dork like me, feel free. So I'm using, again, the if function. The if function says, here's my test, and my test is exactly what I did here. I tested if p was less than alpha. So if p, which is this value right here, if my left-hand p is less than alpha, then I want to reject. Otherwise, I fail to reject. So again, reject, you have to put it in parentheses, otherwise it won't, or in quotation marks, or it won't work. And then if not, fail to reject. I did the same thing here. If J9, if this value is less than alpha, then I reject, otherwise I fail to reject. And if this value is less than alpha, then I reject, otherwise I fail to reject. So again, me being a math nerd, but feel free to nerd out with me. Now we have one more example to do, and that is a hypothesized test for proportions. Let's take a look at our last question, and we have a couple of things that are different than what we've dealt with in our first two examples. First of all, we're dealing with proportions. So in our means question, we were just given the sample mean, or we could have been able to actually compute it ourselves using Excel as we did in the last couple of weeks. I didn't give you one of those this time around. In this example, however, I am given the value out of the total number, but I'm not actually given the p-hat, so that's something I have to compute myself. The other thing that makes this one different is that this is going to be a two-tailed test. So let's talk about what the question is asking. We're looking at an Apple Watch and the health app in the Apple Watch that reports to users of the Apple Watch that they have an irregular pulse notification, which is indicative of AFib. So they are reporting that 0.5% receive that indication that they have an irregular pulse. So according to Apple, our null hypothesis is that nothing has changed, that p, not mu, because this is a proportions question, that p is equal to 0.5%. So be very careful, because one of the common mistakes students make is to say p is equal to 0.5. Now, 0.5 is 50%, not 0.5%, so I'm going to call that 0.005. Now, as we read through the question, it says, cardiologists are concerned that the reported percentage of people receiving the notifications is not accurate. It doesn't say cardiologists think that more people are getting this, or cardiologists think that less people are getting this. It just says not accurate, which means our alternative, the one that we're testing, is simply that it's not 0.005. So what you're going to find as we're looking at this is that we're looking for, is our observed value too far away on the left or too far away on the right? That's why it's called a two-tailed test, because you're going to have an area on each side of your graph, which means the area is going to be a bit larger. And in fact, what we know is that the area of these two tails is exactly the same. So what we're going to do is we're just going to find one of them and take 2 times whatever we find. But let's get back to the question at hand, and then we'll get back to that picture in a little bit. We know that the doctor conducts a simple random sample of 2,315 people. So 2315 is n, who own Apple Watches, and ask if they've received a notification of an irregular heartbeat. 9 of them said yes, so that's x. Notice I haven't found p-hat yet. I'm going to have to find that myself, and so p-hat, which is my observed value, is going to be x divided by n. 9 divided by 2315. The only other thing that we're given is our level of significance, which is alpha, is 0.01. So from here, let's go ahead and find the z-score. And if you'll remember, the z-score is the same as the z-score for a mean, so we're still in the numerator taking our observed value, in this case p-hat, minus my hypothesized value, 0.005. But now I have to divide it by the standard deviation. Now for a mean, it's different than a proportion. And when we did a confidence interval, we found the standard error. And that standard error was p-hat, 1 minus p-hat, divided by n and the square root. But for a hypothesis test, we actually are going to use the standard deviation, which instead of using p-hat, just uses p, which is our hypothesized value, and 1 minus p and n. So be very careful there. So as I'm entering this value, I'm going to find the square root of 0.005 times 1 minus 0.005 divided by n, which is 2315. So my z-score is negative 0.76. Now, here's where you have to be real careful. I just found the z-score of negative 0.76. The positive counterpart to that would be positive 0.76. And what I want to know is the probability that z is less than negative 0.76, and I'm going to add to that the probability that z is greater than positive 0.76. So less than the negative and greater than the positive. Now, again, I know that those values are the same, so I'm going to take whichever one's easier to compute, and then I'm going to multiply it by 2. So if my probability is one-tailed, this is the negative value, I can take norm s dist of that value, and that's going to give me, and of course cumulative is true, that gives me that this area, this probability on the left-hand side of the negative is 0.224. And then I'm just going to take that times 2, because the probability on the right is exactly the same. So now I have all the area of the entire shaded region, which is the probability. Now, what's my conclusion? I'm using a 0.01 level of significance. Remember, I'm looking for, is p less than alpha? Well, p is 0.45, alpha is 0.01. So p is not less than alpha, so I have to fail to reject. This evidence does not support the cardiologist's claim that the percentage of people is not 0.5%. So let's talk about how you can do this in Excel, because this part's a little bit tricky, and again, don't feel bad if you can't do it, because when I give you a question like this in your project, I'm going to have you just find the one-tailed and take it times 2. But I know some of you are math nerds like me and want to be able to set up your spreadsheet. I'm going to go ahead and enter our values. So the hypothesized proportion is 0.005, x is 9, n is 2315, observed proportion is 9 divided by 2315, and alpha is 0.01. So I have everything that I need. Now let's talk about my formulas. The z-score formula is exactly how I found the z-score before. I just pointed it to the correct cell. Again, the tricky thing about that is to make sure that you're using the square root of p times 1 minus p over n as opposed to using p hat, common mistake that I see students make. To the left, I'm just doing norm dist to the left of my z-score. To the right, I just did 1 minus to the left, because obviously those two add up to 1, but I also could have done 1 minus norm s dist of my z-score. And the two-tailed is the tricky one, and that's why I kept putting it off. So again, you have to be super math nerd status to be like, oh cool, let's do this. But I'm going to show you for those of you who are super math nerd status. So I'm using an if formula, and I'm saying if H8, so H8 is the z-score. If that is negative, if it's less than 0, then I'm going to take 2 times norm dist of that, which this part is essentially the area to the left. So I'm saying if my z-score is negative, I want 2 times the area to the left. If it's false, so if the H8 is greater than 0 or positive, then I want 2 times the area to the right, and so the area to the right is 1 minus norm dist. So that's all I did. It's not too tricky. Whoops, don't do that. It's not too tricky, but you could also just take 2 times whichever one, is appropriate for your question. And then, of course, I again math nerded out for the reject or fail to reject by comparing it to alpha. So again, hopefully that gives you a good idea of hypothesis testing for one sample. Next week, we will look at the same exact thing, but for 2 samples instead.